Hello, my name is Riley Hales. I am a graduate student in Civil and Environmental Engineering at Brigham Young University. This presentation is for the Fall 2020 AGU meeting, and I'll be presenting research I've done to make large-scale hydrologic models and services applicable as actionable information through some novel calibration methods. The motivation for this is quite simply that there's a growing demand for water and water information. Changes in climate present potential for changes in the frequency and severity of floods and droughts, and we need to be prepared for that. Hydrologic models will be an essential component of our preparation for those things. My research has taken me to places around the world that struggle with having enough physical infrastructure of monitoring stations and software infrastructure of well-developed models to deal with these kinds of challenges. My goal is to help people in these kinds of situations get the information they need to handle water challenges using whatever infrastructure they have, combined with global scale modeling and services. The problem is that these large models can be really difficult to calibrate and validate, and that gives people an understandable sense of skepticism about how useful the model can really be. So traditionally, you would try to fix the model itself. You would calibrate the model parameters, look for better input data, adjust your land surface model, try getting observed data to run data assimilation algorithms, use that same data to perform validation studies. And these are both very important steps, but what I'm about to suggest is not a way to do those things or something that replaces that. These are really important, but within the confines of the amount of data that you have, the resolution of the models, the time that you have to run these models before you need useful information, it's just really difficult to do. And the data doesn't always even exist, so it sometimes may not even be possible. So what I'm going to suggest is more of a companion method, something that you can use in addition to pursuing traditional methods to improve your model. There's the famous quote, "All models are wrong, but some are useful." And so the inspiration really comes from this approach that the model is wrong, but what if I had a way to characterize how the model was wrong such that I can use my theoretical understanding, use the science of hydrology to deduce more what the model should have been and therefore arrive at a useful conclusion and something I can make a decision on. Let's start by describing what you need to use this method. You need the model's network of stream segments and subbasins as a shapefile or some format that you can use in a GIS software. There needs to be some sort of identifier for each of the stream segment subbasin pairs. You need to know where the observations were made and the name or identifier of those stations. You need model simulated discharge for as long as you can get it. Ideally, we're talking a few decades of historical simulation data, and then as much historical observed discharge as you can get. Now let's go over the adjustment mechanism. We're going to be using a kind of frequency mapping which has been suggested and evaluated by past researchers. So suppose I have some discharge data. I can compute a flow duration curve for that. For any given flow on my simulated discharge hydrograph, I can map it to a corresponding exceedance probability on that flow duration curve. Now suppose I have some observed data for that same point on the river. I can also compute a flow duration curve for that observed data. Now my simulated probability and discharge pair has an analogous pair on the observed data's flow duration curve. So I replace my simulated flow with the observed flow at that same exceedance probability and plot that for every point on the simulated hydrograph. So I start with simulated flow, figure out its exceedance probability, replace the simulated flow with the observed flow with the corresponding probability, and then I plot that. To preserve the seasonality of flow, we usually do this on a month-by-month basis. And this works great for using sparse historical data to adjust a more complete, longer-range historical simulation, but this only works at a single point where you already have some observations. And since the ungauged basins will have different magnitudes of flow as the observed data, we can't directly use this method on basins that don't have gauges, even after we characterize the biases in the model. The solution to this is we're going to create what I call the scalar flow duration curve. We get this by dividing the simulated flow duration curve by the observed flow duration curve at every point, and what results from that is another flow duration curve, except that on the y-axis you'll notice that we don't have a flow, rather we have a ratio of flows, which we will use to adjust simulated flow values. But on the x-axis we maintain an exceedance probability. So then rather than map our simulated flows to an observed flow, we will map simulated flows to one of these adjustment factors. To expand this to the ungauged streams and basins, we're going to need to know which ungauged basins ought to be paired with each of the observed basins that have this scalar flow duration curve. And this is where the characterization methods come in. We're going to start with machine learning, use that to feed spatial analysis, and the results of those two things will help us create those pairs of ungauged basins being paired with a observed basin and its scalar flow duration curve. And then we can apply some statistical refinements since there will be uncertainty in those pairings. We start by doing machine learning. We're going to use k-means clustering with Euclidean distance measures to group flow duration curves. Before we create the clusters, we normalize the flow duration curves by the average annual volume. We do this because we don't want to group by the magnitudes of flows. We are more interested in grouping by the patterns of watershed response and the seasonality that is embedded in that, rather than the magnitudes. When we perform the adjustments, we will use the unnormalized data so that the magnitudes of flow are present and we get closer to correct water balances. And we're going to do this for the observed data and the simulated data separately. Here's an example of what you might get as a result of the k-means clustering. This is using 6 groups. The black area is actually a lot of individual flow duration curves from the simulation that are stacked on top of each other, and the red line is the centroid of the cluster that those black lines got mapped to. Deciding how many groups to create is an iterative process, and that requires checking with your results of the spatial analysis to get right. In the spatial analysis segment, we're going to use the geospatial context of the stream segments in combination with the machine learning results to know how to pair the ungauged basins with a gauged basin and its scalar flow duration curve. We start by computing several attributes for each basin if you don't have them already. That would be the stream orders, the drainage areas, and stream connectivity information. Then we look for 3 groups of watersheds, and I'll list them in order of the confidence of the matches and quality of the resulting model adjustments. Obviously, basins which contain a gauge are the best matches. Next, basins which are directly upstream or downstream of a gauge, usually limited to segments of the same stream order, which are upstream or downstream of a gauge. And then last, basins which were clustered together, some of which must contain a gauge. In this last group, we use the GIS properties to help decide which simulation belongs with which observation. We favor matches by the best combination of close spatial proximity, shortest direct connection on the stream network to a gauge, same stream order, closest drainage area, and so forth. Here's a demonstration of what the results of this step look like. This is in Colombia in the Magdalena River watershed. We're going to start by zooming in, we'll turn on the stream segments and the locations of the observation data. Now we're going to start coloring rivers in the watershed, and these colored groups represent the results of these steps. So they were grouped to the same observation data for correction based on their spatial characteristics and the machine learning results. And our results is maps that look like this. Every stream segment has been assigned to one of these colored groups, and thus to an observation point. Now, our confidence in the quality of improvements will vary based on what justification we use to pair that ungauged basin with a gauged basin. So we can perform some additional refinements. We'll fit our adjusted results to a known distribution. So if flows get too small or too large that they are uncharacteristic of our watershed based on our adjusted results, then we can replace those uncharacteristically large or small results with a flow that fits the Gumbel distribution or some other distribution. And we can also adjust the hydrograph so that the cumulative volume is more comparable to other streams of the same or similar drainage area and stream order. Let's go over an example of what this looks like now that we've gone through all the steps. In blue is the simulated data that we started with, in purple is the observed data. That purple observed data spans a really long time period, but there are gaps in it. And we notice that the simulated data is on average much larger than the purple line across the entire time spectrum. So after we go through each of these steps, we end up with the green line, which much better fits the range of flow values for the observed data. Let's zoom in a little bit more, and we can also see that we filled in the gaps of our observed data. Just because we don't have observed data or there are gaps or something like that, we can still adjust our simulation value across the entire time period, so we can fill in gaps in observations. Here are some statistics that were computed based on this example I just showed you. A few worth mentioning: the Nash-Sutcliffe efficiency increased from negative 114 to about 0.5, a really significant improvement. And we brought our mean absolute percent error down from 224% to about 15%. And this makes sense since our model was really biased high to begin with, and our observation data was much smaller in a narrower range of flows. So our frequency mapping really brought out a lot of that over-predictive bias. Here's another example. In this case, we have the blue is simulated data still, and here observed is green. And we see that the blue is biased high in a few places on the peaks, but actually a lot of the time it is beneath the green line, so it's under-predicting. And after we go through the calibration steps, we end up with this red line. And we see that we have exaggerated a few of the peaks, so we have more peaks above the green than the blue did originally, but they all stayed within a reasonable range for the green value. And we brought a lot of the area where we were under-predicting, we've brought it closer to the green line, so we don't under-predict nearly as much as we did before. Zooming in, we can see this just a little bit better. Here's some statistics that were computed for this example. Since the model did much better to begin with, the improvements are not as dramatic as the first example, though they still improved. We brought our Nash-Sutcliffe efficiency from negative 0.65 to negative 0.15, a pretty good improvement there. And we brought our mean absolute percent error down about 8%. Again, these are still good improvements, and we have better confidence in this result, but they are not as dramatic as before since the model did better to begin with. So in conclusion, this method gets you closer to accurate results, even though the model has biases and errors, though the model still should be refined and go through the traditional calibration methods to try and eliminate as much of that bias and error as possible. But this is particularly useful for the end user that needs to make a decision for their watershed but doesn't have the calibrated model ready for them. These machine learning and spatial analysis steps that I've outlined occurs just one time, and the resulting list of each of the ungauged basins to an observation data set can be used to correct historical simulation and forecasts that result from the same model. A formal validation study of this methodology is ongoing at BYU, including evaluating the various methods for performing the spatial analysis steps. The quality of the improved results varies somewhat by the size of the watershed, the quantity and quality of your observations, and other factors, but overall this method shows improvement and promise, and we are excited to continue pursuing that. Thank you very much. I look forward to seeing you at the AGU meeting in a few weeks.